Let's start the new chapter, alternating current. See this alternating current in a short form, and it is very well known as AC. This AC stands for alternating current. In the previous semester, we have discussed about the direct current, means DC. And in this particular semester, we are going to study the alternating current. So before we start our chapter, it is necessary to know the difference between the alternating current as well as the direct current. So in the direct current, if we see the voltage versus time graph, here I have put voltage on y-axis and time on the x-axis. Then in the direct current characteristic, the voltage will not change with respect to time. And here Vm stands for the maximum voltage or the voltage applied to the circuit. So in this case, the voltage is not changing with respect to time. And in the alternating current, if we see the same characteristic, so this is for DC, and now for alternating current, this voltage is continuously changing with respect to time, either sinusoidally or anti-sinusoidally. So this is the current characteristic or voltage characteristic for alternating current, and this alternating word is used for this voltage is alternating with respect to time, and the magnitude of voltage is remaining same on the positive side as well as in the negative side, and this alternating current is used in our domestic electricity purpose. So one question I am asking you, that which current is well known for the purpose of electricity shock, or we can say which of the AC or DC current is helpful in the shock treatment. So see, if you say this DC current is helpful, then it is wrong. Why? Because here the voltage is continuously applying, and if you see in the AC current, then at this particular time or this particular portion there is no voltage is applying, and so we can save our body from the shock due to this zero voltage. There is only occurring in the AC current, or we can say at zero DC current. In the both case, it is helpful to prevent from shock. And now we will start our analysis by applying the AC circuit analysis. So we start to understand about the alternating current circuit, which is made up from the combination of this L, C, R. So what are these quantities L, C and R? Here L is inductor, C is the capacitor, and R is resistance. And you can see from this figure a series combination is formed using these three components. Now, if you not apply any voltage to this series combination, then there is no meaning of such kind of arrangement. And so we are applying here the voltage V, and here the voltage is given in the cosine function. So the voltage applied to AC circuit is given by V is equals to Vm cos omega t. Now it is necessary that you should understand each and every quantity. This Vm is the maximum voltage, what you have earlier seen in the characteristics of AC and DC graphs. Here omega is for frequency, means the frequency of voltage, and T stands for time, for which time you are applying voltage. From this voltage applying, and remember this is the AC kind of voltage because cosine function is arising over here. And now when this voltage is applied to this circuit, then current I at time t is following or it's flowing to this circuit combination of LCR. So after switching on the voltage, IT current is flowing in the circuit. So which kind of effect you will observe in this circuit? So first of all, you have to consider some characteristic of this inductor, capacitor and resistance. So for that, I am consider over here that my inductor is having 0 ohmic resistance. And the other two combinations, a capacitor and resistance, is having 0 conductance. So with this condition, now I am starting my analysis that after this current is flowing in the circuit, means in this circuit, the charge deposited on this capacitor. First of all, I start my analysis on this, on the capacitor. Because capacitor we know, the work of capacitor is to store the charge for a particular time interval. So I am supposing that capital Q is the charge that is deposited on the capacitor. That is equal to capital Q. Now, as there is conductance and resistance, so there will be some amount of current will be changed. That means there will be a rate of change of current, and I am denoting that rate of change of current as di by dt. Now, if we see the voltage passing through the inductor or the voltage of the inductor means VL, so which kind of voltage you will get? So the value of inductor into the rate of change of current. So VL is equals to L di by dt, and here you are actually applying the Kirchhoff's law remaining. And so for remaining quantity means for capacitor and resistance, therefore the voltage, and here voltage is actually the potential difference between two ends. See, the capacitor is like this. So the voltage difference between these two ends or the potential difference between these two ends is given by Vc, and according to Kirchhoff's law, that is charge deposited on the capacitor and divided by the actual value of capacitance, that means capital C. Now the current flowing through resistor, that is very easy, the voltage flowing through resistor, that is given by Ohm's law, that is VR is equals to IR. And now with the help of these three equations, now I am applying Kirchhoff's second law. So what you will get? The total voltage is V, and the voltage is dividing into the circuit components of inductor, capacitor plus resistance. Now we have all three values of VL, VC and VR, as well as we have the value of the voltage or the AC voltage passing through this circuit element, that is Vm cos omega t. So let's substitute these quantities in equation number 1. So left hand side will be Vm cos omega t. The value of VL is L di by dt, plus the value of Vc is Q over C, plus the value of VR is IR. Now if you see, I is equals to dq by dt. The value of I is equals to dq by dt. And so if you differentiate it again for substituting the value of di by dt is equals to d square q divided by dt square. And therefore Vm cos omega t is equals to L d square q by dt square plus q by c will be as it is, plus r dq by dt. So actually we are moving to obtain the differential equation. Now what I am doing, I am dividing this particular result by the inductance or the value of inductor L. So I am writing over here, dividing above equation with respect to capital L, and therefore Vm by L cos omega t is equals to d square q by dt square plus r by L dq by dt plus q over Lc. And this equation is very useful because this is the differential equation for the charge q, because you see over here the charge is differentiating every time with respect to time for which voltage has been passed. And so I can say this is the differential equation for the charge q, and this is particularly for AC circuit. Therefore, the above equation is the differential equation For the charge Q, of AC circuit. Now, if you see, this equation is containing mechanical quantities, while in the differential equation of LCR circuit or LCR series AC circuit, there are electrical quantities. In standard 11, what equation you have studied, that was containing mechanical quantities, and here the quantities are electrical. So let's obtain the actual quantities which are mechanical and electrical. So here is the table for mechanical quantity and electrical quantity. Here the mechanical quantity is displacement Y, and correlated to that the electrical quantity is electric charge Q. Similarly, over here the velocity is the mechanical quantity, and here the flow of charge, that electric current, is electrical quantity. Resistive coefficient V, so here the resistance. Mass M is related to the induction or inductance L. Here the force constant K, and here the inverse of capacitance. Angular frequency under root K by M, and here angular frequency is under root 1 upon LC. Also the periodic force, and here the periodic voltage takes place. And so now we have obtained this equation, so it is necessary to find out the solution of such equation. So with this, our article number 2.1 and 2.2 is over, and now we are moving to the next article number 2.3.